is the resistors in series. What rules do you apply? Can you remember? Anyone? Constant what? When the resistors are in series. Hello? Constant current, right? When the resistors are in parallel, you apply constant voltage rule, right? Yeah, some of you are remembering. Okay, so shearing stress is the same. Okay, I'm going to write you 5 rules, and I'm going to show you how these rules are derived. Then you can solve shearing stress. Okay, as I say, it's one of those topics that a lot of universities, when in this topic, a lot of universities will avoid. Okay, I've checked with my colleagues at other universities. Okay, they avoid it. The only university that does very similar level and slightly tougher is in which university? I talked to the prof. We're at the same page. Hold on. It's one of the top 5 in the US. The name Duke University, DUKE. Okay, we are very similar level at that level. Okay, let's go. Okay, so what are shearing stress? Okay, so shearing stress stresses acting parallel to the surface. Okay, so those of you that have done 3C with me, I've done this very briefly when we did Mohs circle. Okay, so I'm going to go into more detail. Okay, right. So if we have a transformation over here, so this is our X, this is our Y, and then we have an element. Okay. Right, we have an element. So shear stress are applied parallel to the surface. Okay, so we have so this is our shear stress. Okay, so the topic before was normal stresses, right? Now this is what? Shearing stress, right? You can see how we're going to assemble the big picture already. Then after this, we are going into what? Mohs circle. Okay, you can more or less, so we're halfway there, so that you can design a structure that, or you can calculate, you can analyze a structure that you have confidence to determine the material to select or the geometry to use. Okay, so the arrow that I'm highlighting in yellow now, this arrow is equal to shearing stress. Okay, the first X is the intersecting plane. The Y is the direction of the shear stress. Okay, so the X over here is the intersecting plane. So what do I mean by that? Okay, if you take this line over here that I'm highlighting in blue now, right, and you put on the transformation, right, the line will be down here, or the plane will intersect the what? The plane will intersect the x-axis, right? So down here, the plane will intersect the x-axis. So that's what the first X means. The Y over here is related to the what? Direction of the shear force or shear stress. Okay. So this arrow is shear XY, the other one. So the shear stress, the one at the above, is a shear stress intersecting plane, okay, which I'm going to highlight in yellow now. This plane over here will intersect the y-axis, and the direction is in what? X. Okay, so I'm not going to tell you what is positive shear and negative shear yet. Okay, I'm going to do the notation first. Now, if we were to do this 3D, okay, we were to do this 3D. So I'm going to sketch 3D now. So again, this is our X, Y, and this direction is our Z. So now we are going to draw a cube now. Okay, now we're going to sketch a cube. Okay. So that is our cube. Right. Before I go on, okay, in shearing stress, in order to achieve equilibrium, the shear xy must be equal to the shear yx. Always. Okay. Or not, if they are not balanced, and they're not equal, the element will still continue to deform. Okay. So now if we have a cube now, how does this work? Okay. So we know this space. Okay, so I'm going to change color now. This space over here, right, will intersect the x plane. Okay. And the next one over here, this will intersect the z plane. Sorry, wrong use of words. The plane, do apologize. Good morning. Plane will intersect x-axis. The next one, the plane intersect z-axis. And the last one, the plane intersect y-axis. You can see that, right? Right, you are clear on that. Yes, very obvious, right? So now we are going to draw our forces. So this one is our shear x. So shear force is going towards the y. Over here is our shear. I'm going to use different color. Okay, so that is green. So this is our shear intersecting the y. The shear stress is in the x direction. Okay, I'll do another one. Yeah, so this one over here, right? Shear intersecting x plane in the z direction. Okay, then I'll go into the other direction. Shear, the intersecting plane is the plane will intersect the x-axis. The shear force in, sorry, the plane will intersect the z-axis. The shear stress is in the x-axis. And lastly, the one over here, the shear, the plane is in the intersecting plane is z-axis, and the direction is in the y. And the last one now. So I hope you all see the trend. Okay. Right. So there you go. So
Sorry,
most
Eugene.
of, yes.
I know that I know why you're saying intersecting a particular axis and then saying which direction it's moving in. However, how do you know which of the axes it's intersecting? Because if you have a vector going in the y direction, it will intersect both the x and the z axis.
Z and x axis.
So you have two y vectors here, one in blue, one in red, on either face of the cube. And you have one intersecting the z axis and one intersecting the x axis.
Yes.
So what differentiates them?
So it's the surface area. So this will intersect the x plane, right? Right. The
I
one
see, and
that
you're
goes.
using x as the normal. I see.
Yeah. Okay. So that's the plane is intersecting, right?
Okay, thank you, sir.
Intersecting the axis. Okay. Right. Okay. So now, how does things feel in the shear? Okay. So I know shear stress is just okay, shear stress is failure, but how does it actually feel? Okay, and that is very contradicting. Okay, if you don't visualize it, or if you can't visualize it, you don't know what you're calculating. Okay, so let's look at failure by shear force. Yeah. So now if we have a cantilever beam, okay, and the cantilever beam is made of layers, All right, 1, 2, 3, 4, 5. Okay, they're made of layers like this. Okay, and all these layers they can slide past another. Now this is a schematics. All right. So when we applied the load, down here, known as V. Right? We applied the load in V. So when the structure deform, okay, so this is deformation pattern. Okay, so I'm going to sketch our deformation pattern. Okay, so the deformation pattern will do this. Okay, so you have one here, and you have one here. Okay, and then you have 1, 2, 3, 4, 5. Okay, so 1, 2, 3, 4. Oops, the last one I lost concentration. And 5. Okay. Okay. So you can see that the failure, right, along, okay, shear stress. Okay, this is what I'm trying to get at. Okay, if you look at where V is applied, the shear stress is in this direction, right? So if I draw my transformation, right, this is X, this is Y, this is rotation in our Z, right? That is how the shear stress due to V will initially react. So this is shear, right? Intersecting plane is X, the direction is in the Y, right? So from what I told you guys earlier, that you have a counter reaction, right? So this is shear, intersecting plane is Y, and this is X. Okay. Now the question to all of you is this: which component will generate the failure? Shear XY or shear YX? I've drawn for you the deformation pattern. Can you all make a guess which one will induce the failure? Anyone?
Shear XY.
Shear XY. Now, shear XY, my answer to shear XY is it will not fail. Why? The shear XY, okay, the geometry in this direction the geometry did not change. Okay. However, you can see that there is a slip. Okay, there's a slip. I'll call this a slip. Parallel to the schematic layers. Okay. So the stress that will induce the failure is what? The shear yx. But we are lucky. Lucky in the sense that shear xy is equal to shear what? Yx. Right?